Hello everyone. In this video we are going to look at a topic that I'm sure a lot of you might be interested. It's called transfer learning. And you can use it for different types of networks, but it's very common for convolutional neural networks that are for object classification, especially images. It has been used a lot in CNNs, and the idea is if I learned something with a bunch of images in the past, if I have trained a very successful CNN with a ton of data and it has been shown to be very effective, now if I want to classify two new sets of objects that were not in my training set, what should I do? Right? So first of all, these training image data sets that some of these networks are trained on, they have millions and millions of images. Like for instance, the ImageNet is one of the major ones that has more than 1.4 million images, average size of 469 by 387 pixels, and it has more than 1,000 classes of objects. Now let's say you have two new classes of objects for your application and they are not in the ImageNet. What would you do? First of all, let's say here, if you have 1,000 classes and 1.4 million images, that means there is at least 1,400 images per class. So now if you have two new classes, that means you need about 2,800, 3,000 images. You have to get them with all sorts of varieties and so on. Add them to ImageNet, retrain that pre-trained network, whatever it is. One of the famous ones is called Visual Geometry Group, or VGG. There is MobileNet, which we're going to see today, trained by Google. There is Inception, there is ResNet, and so on. And retrain these networks, that is not an easy job. Some of these networks, like this MobileNet, it has more than 160 layers. It's not just a few layers. And training that needs a tremendous amount of resources that might Google only have. You don't, so that is not feasible, okay? So what would you do? The idea is this. They say, hey, look at some of these CNNs that are already available, as I said, like this MobileNet or VGG. If you look at them for different classes of object that they have been trained on, like for instance car images, or let's say elephant, chair, whatever, if you look at the initial layers of the CNN, the initial layers have extracted very similar features. I mean, if you look at, like here, like it's the first layer of the CNN, right? As we looked at them, the first layer or first few layers are basically extracting like edge detectors, corner detectors. And as you go up through the CNN, you get bigger features that are more related to that specific object, right? But still, you see similarities, right? Still, if you look in the middle layers, you also see similarities. As it goes to the very top layers, right before classification, dense layer, you see now they start to look a little bit different. So the idea is, hey, can we use these convolution layers of these pre-trained networks, not touch them, only change the last couple of layers that are used for classification, and train those. So if I have images of dogs, right, if I pass it images of dogs, with the same features that I got from that pre-trained network, can I go ahead and let's say identify that, hey, this new class of images is a dog or a cat or whatever that was not in that big training set like ImageNet or something. Can I do that? Can I transfer what I learned, which are these weights and biases of these convolution layers? Can I transfer those learnings to some new class of data that was not there and do a proper classification? That is called transfer learning. Okay? So how do we do that? So as I said, this is the a classical convolutional neural network. As you can see, it has a bunch of convolutional layers. You see in green, it has these pooling layers in red. You might have Bayes normalization layers and so on. And at the end, you might have your dense layers and the softmax. If you have several classes or binary, you might have a sigmoid function. So this portion of the network that you don't want to touch and you want to use it as is, this we call it the base, or the base model. We want to use these and not touch them. This new portion that you want to retrain to identify the new class of data, this is, we call it the head of the model, and we want to retrain this. So you see, as we go from here to here, we keep the base intact, but replace that head part with some new thing, and all of these weights are now unknown, but by passing these new training and test set for these new classes of data, we hope that we can train them to do a proper classification. Okay, now to give you more motivation, one of the motivations is many of these pre-trained networks like VGG, ResNet, MobileNet, and so on, okay, which are trained on huge data sets like ImageNet, and they won the competitions for ImageNet because this ImageNet has competitions each year, and the new trained networks will see if they can do a better job on the ImageNet. Many of these pre-trained networks are available in TensorFlow. You don't need to go and find, hey, Google, give me your MobileNet. They already have it, okay, because TensorFlow is also for Google, so Google has lots of these pre-trained networks available, so you can just import them into TensorFlow. So simple, okay? So now you can go ahead and get a bunch of new images from these new classes, as many as you have, as many as you can get from the web, just as many as you can. You don't need to have several thousand images per class. And if you don't, to improve your results, you can use what? You can use the data augmentation technique that I talked about in one of the previous videos, and we're going to see it again today, or Bayes normalization, or both of them, to improve your results. So gather as many images as you can for the new classes of data, and then retrain the head of those big CNNs on this new data. So with a small time for training, you should be able to achieve relatively good accuracy, okay? So one important thing is, as I said, this base model, you want to lock it, okay? You want to lock this guy and not allow anybody change the weights of that. That we call freezing. So that base, you're going to freeze. You're not going to allow the weights and biases to change. How would you do that in TensorFlow? I'll show you, okay? Now, this way, as I said, you're going to spend a small amount of time and memory, and hopefully you achieve high accuracy. Now, not only if you allow these weights to change and not freeze it, it is going to take a lot of time and a lot of resources to train that huge of a network, and you might not do it. Another reason is, remember the Bayes normalization layers that I told you? Remember the goal of them was to get the average and standard deviation of the data, normalize them, and transfer them to a new set of data with new average and new standard deviation that can perform better with the convolution networks. Well, remember, those means and standard deviations were calculated based on the results of these convolution and pooling layers. And now if you change them, guess what? All of those mu's and STDs and sigmas that they learned, A's and B's, all of them, they have to be recalculated too. They are not going to be any useful. So you have to be very, very careful, even if you have resources, and even if these networks are not crazy big, you're going to have a lot of work to do. So you better freeze really the base of the model, okay? So this is the basic idea of transfer learning. Now, one more thing that you might say is, hey, look here. These very top layers of this convolution networks that are trained, they are not really similar. And they shouldn't be because they are identifying different classes. I mean, yeah, these initial ones are very similar. The middle ones could be relatively similar, but these final ones, here is a car, and here is an animal, and here is a chair. So if I pass a dog this time, right? If I pass some dog, and I'm not the best at drawing, so sorry, it might be like a dinosaur or something. But if I have a dog or a cat or something, this is quite a bit different than those, and I might not get a good accuracy. So what can I do to still not train the whole base, but get some better results? And your idea might be, hey, I'm not going to train the whole base. I'm going to keep this portion of the base and freeze that portion, but this top portion of the base, I'm going to retrain it. So only what? This time you might think, well, this time I want to only freeze this portion and retrain this guy, as well as this one. So do a little bit more training, but only train these top layers, the top of the base, that first of all, they don't have a ton of weights, and second of all, there are not a ton of layers. This way, those high-level features that are not similar, you can get rid of them and retrain them for a dog or a cat, or anything else that is new. And this way, we call it fine-tuning, and this way you can achieve a lot better results. Okay, so I'll show you how to do transfer learning, as well as how to do what? Fine-tuning, and training a little bit at the top of the base as well to get better results. So here is the TensorFlow code, and I wanted to let you know that the code I borrowed from the TensorFlow documents itself. So I did not write this code, okay? I just borrowed it. I did a little bit of changes in it. I made it simpler. I added a lot of comments and everything, and I'm gonna explain it to make it easier for you to understand. But the original code is from TensorFlow, and my goal here is to explain the portions of this to you. So the libraries you need is, of course, NumPy, Matplotlib, TensorFlow, and the sys and operating system for adding directories. So the first thing you need to do is to get the data for cats and dogs, and to bring in the pre-trained network MobileNet. So here I go to Google Pictures and I get 3,000 images of cats and dogs. At this URL, I use the method called tfkeras utilities get file. I pass to it the URL. I basically tell it some path, okay, path to zip, which is cats and dogs.zip. Say, go and get this guy from that URL and make sure you also extract it. Okay, so this method will download the zip folder and extract it for me. Then what do I say? I say go ahead and add what? Add to the current location OS path dir name to the current location, which, by the way, if you print it, it is here. It is under root.keras.dataset. Under this location at this path, you add this extra name to it. So create a new folder called cats_dogs_filtered. So now you're going to get something like this. And what? When this you use this join, it adds a backslash, and then it adds this name to it. So you create this folder basically. Okay, and then what? Now, in that folder, I also want you to have two subfolders. One is called train, one is called what? Validation. Okay, so here we want to have two different folders under where the zip folder is going to be, the files are going to come from that. One is going to be what? Is going to be train. The other one is going to be what? validation. So you have to have an organization for your data, okay? You don't want to bring all of their data and just mix them and put them in the same folder. You have to have a separate folder for training, a separate folder for what? Validation. So you click on that, it brings them, it creates those folders for you, download the zip folder, extract it, and so on. Now it is time to what? It is time to basically populate your training data, validation data, test data into those subfolders, okay? And if you want to add augmentation to add more layers, more images to your training set or anything, you want to do that, and you want to do it in batches, okay? So your training here is going to be done in batches, not one by one. So each batch of images will contain how many images? It's up to you. Here it's suggesting 32 by 32, and the image size is expected to be 160 by 160. So what do you say? Use this method called image underscore dataset underscore from underscore directory. Go to the train dir, which is basically what? This address. Go to that address. Then what? Make sure you shuffle the images. Grab a batch size of 32 images and make sure you resize the images to 160 by 160. These images that you got from Google, there might not be all 160 by 160. But that's what this ImageNet is, this pre-trained network, this MobileNet, it expects 160 by 160, so I'm gonna resize them to the appropriate size to be used along with that pre-trained network. Okay, so I go and grab batches from the train directory. I also grab batches from the validation directory, and I call them train dataset and what? Validation dataset. Now, if you watch my original videos under playlist machine learning, you know that there are three types of data in a neural network. There is training, there is validation. Validation is to make sure that you are not doing overfitting, and then you also need test images. Okay, so you need training, validation, and test. Now this set of images that we downloaded, they don't have test images. Okay, they only have training and validation. So here we can go ahead and allocate a portion of the training images to the test. How do we do that? Here we go and say 20% of the data, go ahead and give them to what? Give them to test, or you might go 30% or whatever you want. So what do we do? Here we go to the validation data set and use this method tf-data experimental cardinality. And then from the validation data set, so we use, so here when it says the data, it's the validation data. We are going to use 20% of the validation, not the training data set. We're going to allocate 20% of them using the take method. I say validation take, val batches divided by 5, the rounded version of that. Go ahead and pass them to test data set, and the skipped version, which is the other 80%, pass them to the validation data set. So you see, I break down this big validation data set, which was 1,000 images. I break it down into basically 200 test images and what? 800 validation. How many training data sets you have? There are 2,000 images. Okay, so you have 2,000 images training, 1,000 validation, which now you break it down into what? 200 and 500, 800, I'm sorry. Okay, so I added those comments for you. Good. Now, here is an extra step to optimize the performance of grabbing batches, and this is using what we call buffered prefetching to load the data from this address here, okay, without blocking the other I/O. And this is just an extra step if you want to accelerate the grabbing of batches from the disk here. okay, or in this case the address under root. So here you say autotune tf data autotune, and then when you grab the train set, validation set, and test set, you use this method called prefetch. And for buffer size, you use the autotune. So you don't give it a fixed buffer size, you give the autotune, and here it can do optimized performance for grabbing the batches. Okay, and I don't want to get into depth of that. This is just to optimize the performance of grabbing images. Then to make the training set more, you use data augmentation. So you create a layer. Here you don't apply the data augmentation here. You do it later through the network. You just create a layer. You create a data augmentation layer from TF Keras sequential. Under TF Keras layers, use a random Philip horizontal. So you randomly Philip it about the horizontal axis, some of them not, and then random rotation. So here you need a random rotation 0.2. Okay, so this 0.2 is a ratio between 0 to 1, which allows some random angle to be allowed for rotation. Okay, so one thing we did for the dogs and cats training data to work with the MobileNet was to rescale them to 160 by 160. The other thing is to rescale the pixel values, because MobileNet was trained with pixel values between -1 to 1, but the cats and dogs images were in range, or they are in range 0 to 255. So we need to change those pixel values, and there are two ways you can do it. Either use the pre-processing input layer from the MobileNet v2 itself to take care of that, or you can use the rescaling from under Keras under layers and tell it to divide everything by 1.27 127.5. You might say, where did you get this number? Well, this is exactly half of 125, and then give it an offset of -1. So what does that mean? It means pixel new equals what? Equals pixel old divided by 127.5, right? When you do that, then the result will be between 0 and 2, and all you need is to subtract the 1, so it goes between -1 and 1, okay? So you can either use that layer from the MobileNet itself, or use this rescaling layer to make sure the pixel values match. Now it is time to what? It is time to form the model. So what do? We bring in, under applications, we bring in the trained MobileNet v2. You see here, this is already available in TensorFlow Keras. We don't need to do anything. So we pass to it an input shape, okay, which is image shape here and image shape. If you remember, we got the image shape up here, right? And then the important thing is here, include top false. Where is top? Top is this portion, as I said. This guy here, this head or top, okay? So if you want, you can call this guy what? Call it top. So it says, hey, do not include the top. Only include the rest of it, which I called what? If you remember, I called this whole thing the base. So it says only include the base, do not include the head. And the weights are, of course, they're all trained on the ImageNet data. So create the base model. Now, this base model is going to extract all of those features, right? It is going to extract all of these features. So what does it generate at the end when you pass to it these images of 160 by 160? Right before this top layer, what is it that you get at the very end? So let's take a look at that, what it creates for us, because we need to know that, so when we define the dense layer, we know what dimension it is taking in. So here, look, I'm taking an image batch and a label batch using the next on the iterator that I'm applying to the train data set. So it grabs the next iterator, and that will basically grabs the next image batch and label and so on, right? So here, look, I applied the base model to that image batch. I just grabbed an image batch and applied the base model to it and call it feature batch. And now I want to see the shape of the feature batch. So if I look at the shape of the feature batch, you see it turns 160 by 160 by 3. It turns it into 32 by 5 by 5 by 32 sets of 5 by 5 by 12 watt AD blocks of features. Okay, so the shape of the output is 5 by 5 by 12 AD. Okay, that's those output of the base model. Okay, as I said, we need that, so we decide on the size of the head. Now, before we go to head or anything, we need to make sure we don't allow the weights of the base to change. So here we say base model.trainable false. I'm not going to allow you to change these weights. Now what? Now let's go and create the head, okay, the top. So for the top, we use two layers, not just a dense layer. We also use a global layer. So we use TF-Keras layer global average pooling 2D. And remember, I explained this global averaging, right? And the reason to do that is to convert what? This 5 by 5 by 12 AD to just 1 by 1 by 12 AD. Okay, so here I have added that for you. So we create this layer and then we apply it to the feature batch that we got from the output of the base model. And we want to see the size of that now, right? And you see the size of that is 32 by 1280. So here it did not even write 1 by 1 by 1280. It just converted it into 1280. Okay, right? So we really don't need this part. It's just 1280. And now when we go to the dense layer, you see here I create a dense layer with just one neuron, because all it needs to do is to basically apply a bunch of weights, right, to this vector here. So it's gonna have only 1280 weights, this dense layer. And then you see here, for prediction batch, I applied the prediction layer to the feature batch average, right, which I got out of the global pooling, and I want to see the shape of that. And now you see the shape of that is what? 32 by 1. Okay, so it converts that 1280 into a single number. 32 of them, but just a single number, right? So that is what your dense layer is doing. Good. So now it's time to what? So here, this part is basically to get some values, to get some dimensions. So now let's basically put this prediction layer and this global average layer and the base model, put them all together along with the pre-processing layer we did and the data augmentation layer. Let's put all of this together and create our network. So here we start with an input layer first. We say that the size of the input is 160 by 160 by 3. So that's my input layer. Then I follow it by what? I follow it by a data augmentation layer, which is applied to the inputs. Call it X, then pass that X input to the pre-processing unit. Again, reassign it back to X. Then pass that X to the base model, training false. You see here, not only I said they are not trainable, I'm not allowing any training to happen here. The result is X. That X is passed to the global average layer. It's X. Then before I pass it to my prediction layer, the dense layer, I also add the dropout layer with 20% chance of being dropped out just for better generalization. Then I pass it to my prediction layer and call it the output. And now I say TF-Keras model inputs and outputs is my model. In the past, the way I did it was using the sequential, if you remember, right? So it was something like this, right? We could do it this way too. This is another way to define a sequential layer, is by passing the output of each previous layer as the input of the new layer, get an output. Again, do the same thing, get this output of this data augmentation, pass it as input to pre-processing, and rewrite it back to the same output and keep going. So what we are doing here is basically the same as sequential, because we are applying each output to the next input and so on. And then the original inputs and the final outputs, you pass it to the TF-Keras model, and that will create the model for you. So these two are equivalent to each other, okay? You can do it this way as well. And this is very common. So now that we got the model, we can go ahead and plot the model, right? By the way, if you want to see how many model trainable variables you have, you see it's 2. The length of it is 2. It doesn't mean there are 2 parameters. There are 2 types of parameters, the weights and the biases. Only for what? Only for this prediction layer. But how many are they? How many of those weights and biases? You have 1280. Okay, and if you want, you can go ahead and plot the model as well. So let me go ahead, and seems like it did not here plot the model. You know what, let me plot the model for you. It might be interesting to see that. This I haven't done in the past. So you use the TF-Keras utilities plot model, you pass to it the model and say show shapes true. If you do that, it is going to show you the type of the combined model you have. So here, look at that. The inputs are 160 by 160 by 3. And then you go through the sequential, which has a ton of layers, as I said, right? So you see math through division, subtraction, MobileNet 2, 160, global, so many things, right? So here it shows the overall shape of that MobileNet here, right? This guy, it's just, it doesn't show all the details of MobileNet, but it just says MobileNet. And then you have your own global average pooling that added, dropout, and dense. And you might say, what is this true division and subtract? This is not MobileNet, so what is this, right? What is this? Guess what? This is exactly this formula that we had. Remember, that's pre-processing. You are dividing by a constant and subtracting a 1. Okay, so this pre-processing unit is what's doing that division and subtraction here. Okay? Yes? Okay, you see that? These two? And here, of course, you get the augmentation data as well. So this is the plot of my network. Now let's go ahead and add the parameters of the network and start training. So here we use a very small learning rate, 10 to the negative 4. For optimizer, we use Adam with that learning rate. For loss function, we use binary cross entropy. Okay, from logits, true. And for metric, we use binary accuracy. Okay. And why do you use binary here? Why don't you use categorical? Because you only have 2 classes, dogs and cats. So it's either dog or cat, so we don't need categorical. Categorical was used in what? Categorical was used in MobileNet. Here, the softmax. Now we have to replace it with what? With the sigmoid. Okay? So that's what we have, and that's why here we have a binary everything. Then we allow the fit model to start working on train data set with the validation equal validation data set and epochs equal to initial epochs. How many epochs do we use here? 10 epochs is enough. And we go with 10 epochs. It goes from a loss of 0.71, an accuracy of 58, all the way to loss of 0.22 and accuracy of 0.9. So here we plot the loss function on the training and validation data. You see they are going down. I can probably even increase the number of epochs, but you see they are kind of reaching at a flat level now, and the accuracy also kind of plateauing. So 10 epochs should be enough. And this is the accuracy on them. Now here, this last part is that fine-tuning I said. release some of the final layers of the base that we didn't touch, let them now be trainable. Okay, so what do? Here, first thing is we have to now allow the base model to be trainable. So we say base model trainable true. Okay, now I'm allowing some weights to change. All of them? No. How many? We'll find out. We here have the control. So here say fine tune at 100. Basically, remember it had about 100 something layers, 160, 150, 160 layers or something. Now only from layer 100 above. We want what? We want to, let's see here, I have a command here that shows me how many layers the base has, right? So if you look at that, let's see, 155, 54 layers the base model has. Only from 100 to 154, I want the weight to change. Anything below 100, I want fixed. So how do I do that? I say for layers in base model layers, from 0 to fine tune at, which is 100, layer trainable false. You see? I first set everything trainable, but now I go back and say from 0 to 100, they are not trainable. Only from 100 to 154 is trainable. Okay, and then I recompile the model. Again, the same loss function. And for optimizer, here I use a different optimizer, RMS prop, which I explained in the past for you. And for learning rate, I use a smaller learning rate. I bring that 10 to the negative 4 now down to the 10 to the negative 5. Want to really fine tune, so I need very small increments in the negative gradient direction. You want to go slower. Okay, and use the accuracy again. And now if you look how many trainable, how many different types of trainable model variables you have, now you should have a lot more. I guess this one was not shown, but if you want, I can run this just separately for you. So you can see that here. Okay, the result is 56. Remember last time this guy was 2. It was 2. Where does 2 come from? Where does 2 come from? Remember we added what kind of layers? We added this prediction layer and global average layer and dropout. Now global average does not really need a parameter and dropout does not, but this prediction had weights and biases. So it has 2 types, and then we allowed from 100 to 154 to be free, so I have 50 more layers. 54 plus 2 is what? 56, and that's this number that you just saw. Okay, so now I have 50 sets of variables, not 56 variables, 50 different sets of variables. Each one, they have their own dimensions, so a ton of variables really, a ton of weights and biases to be trained. And now you see that my loss function already starting at 1584. It was already reduced by the original training. Now I want to further train it. Okay, so what do I do to further train it? One thing I did was I reduced my learning rate by 10. The other thing you want to do is to go more epochs. Originally I went 10 epochs. Now I add another 10 epochs as fine-tune epochs, so my total epochs is going to go to 20. So you see when I pass the training data set, I say my epochs is equal to this 20. My validation is validation data set, and another important thing you add is this guy. I say initial epoch equals R epoch negative 1. What does that mean? Well, R is that model that you already trained ahead of time, right? R is this guy. How many epochs did it have? 10. So when I say R epochs negative 1, what does it mean? It means the last epoch that R had, which was 10. So I say my initial epoch has to be what? 10. Start from 10 and then go to what? To the total, which is 20. Okay, so I don't start from 0 again. I start from 10 and I start from the results of the previously trained network from 10 to 20, fine tuning now. So you see I'm starting with huge accuracy already, right? And with a small loss, and I try to make it better, and it does. Look, it goes from 0.15 to 0.06 and from 94% to 98%. And if you plot this result on the top of previous one, this is what you get. So to the left of the green line was loss function before fine-tuning and the accuracy before fine-tuning, and to the right of it is what? The loss function and the accuracy after the fine-tuning. And you see I could add a little bit more to the accuracy and reduce a little bit more from what? From the loss functions. You might say, why didn't you use 20 epochs? Well, guess what? Because of two reasons. First of all, the learning rate I had was big, so I had to reduce it. Second thing is, these weights from layer 100 all the way to 154, they were not changing. Now I'm allowing them to change. So I have really room for improving the results. In the past, that was it. That was all I could achieve. Now I can achieve more, okay? And the way that I did these on the top of each other here is loss and V-loss that I defined earlier, and accuracy and V-accuracy that I defined earlier, okay? And these are vectors. These loss, V-loss, and accuracy and V-accuracy or val-accuracy, these are vectors. Now I'm gonna add the new results to them. By what? By this plus equal. So I say that R fine is the result of the fine-tuning, the model as a result of fine-tuning. Also add the R fine-tuning history of loss, add this new vector concatenated to the previous loss and the V loss to this. So this is what? This is vector concatenation that I'm doing here for loss and for V loss, as well as for what? Accuracy and V accuracy. And then I add this extra green line here, which goes from initial epochs minus 1, which is at 10, at point x this to the other x. So this is a line connecting from x of this point to x of this point, the same x, and y of them is 0 all the way to what? To, let's say, 0.75 or something. How do I get that 0 and 0.75, the y of these 2 points? Using y-limit command. See, I use PLTY limit. This PLTY limit returns a vector of 0 and 0.75. So I go from 9 and 0 to 9 and what? 0.75, and I add a green line with this label, start fine-tuning, as you can see. So I can put them next to each other. Final thing, I want to run this on some sample images from the test and see in action, did it do a good job on cat and dog? So here, I use the NumPy iterator, and next, remember, that takes the data, and I apply it to the test data set. I get one image batch and one label batch, and then I do my prediction using model.predict on batch, apply it to image batch, and then I flatten it to get a vector. Then I apply the sigmoid function on it, and then I basically round it to either 0 or 1 here. So the answer for predictions is now going to be only a vector of what? Zeros and ones. Now I create a subplot, okay? I create a subplot here, and then I say what? For I from in range 9, so get 9 images, go to that subplot and then show that image. Now if prediction was 0, the text is cat, because 0 is for class cat, and if it was 1, then the class is what? Dog. Use that text on the title. And here are some results. You see here, it predicted the cats very, very accurately. These 3 are cats. This guy is cat, and this one, although this one is quite a bit hard to say really. but these two, this one, and this one is dog. So you see it did an amazing job, right? And I turned the axis off so it doesn't show the numbers on the axis. Okay, so here is some final results. So this is the entire TensorFlow code. Again, it's coming from here. I added a little bit of modification, and I'm gonna share this with you so you can learn from it, and hopefully this is transfer learning from what I learned to what you are going to learn. Thank you so much for your attention. I'll see you in the next video.